and making components. How do I move this forward? There we go. Cool. So I work for a company called Digital Alloys, and we've developed a new type of metal 3D printing process called Joule printing, which has the promise to really be much lower cost than existing metal printing technologies. It is fast, and it can deliver really high quality parts without a lot of post-processing. We're focused on sort of applications that fall into three main categories. One is hard to process metals and expensive metals. So obviously titanium is a key area of our focus for that reason. Another is hard to make designs, which I think you'll see across all of 3D printing. That's really where people have looked to leverage the technology. And then parts that are hard to source because of lead time, supply chain risks, costs, etc. So a quick background on the company. The technology Joule printing was invented in 2014, about 5 years ago. The company was officially formed about 2.5 years ago to commercialize Joule printing. We raised a Series A at that time, and then we raised a Series B round of financing about a year ago, and that includes Boeing, Lincoln Electric, if you're not familiar with them, one of the leading welding technology companies and wire suppliers, and then some typical tech VCs. And right now we're sort of still in development. We're kind of in beta as a company. We have about 24 early access customers, mostly automotive and aerospace, that we are testing, kind of developing the technology with hopes to commercially launch as a parts provider using Joule printing next year, and then start selling printers around 2022 is the plan. So, I mean, I don't know where people's level of understanding of 3D printing lies today, but just to kind of level set, there's sort of three main reasons that people are excited about additive manufacturing or 3D printing. One is to improve products through design, through producing designs that you are not able to produce conventionally. There's some great examples of that in aerospace, using materials like titanium. One, if you guys haven't heard of it, can look up, is the GE LEAP fuel nozzle that takes 20 parts and consolidates it to one, saving production time, cost, improving the quality of the part, reducing the weight of the part. Then there's time savings, and a lot of that comes through the fact that it's sort of a digital manufacturing process that doesn't involve a lot of tooling. We look at a lot of titanium aerospace parts that involve really long lead time forging tooling. It's a way to eliminate that. And then a way to lower production costs, which has been somewhat elusive given that most of the metal 3D printing technologies have been very expensive to date, but this is definitely something that we're attacking. There are a lot of different ways, I know it's hard to see this, but there are a lot of different ways to 3D print metal. It falls under just kind of an umbrella of metal 3D printing, but most people don't know that there are a lot of different ways to process metal with 3D printing, just like there are conventionally. Some of them involve wire, some of them involve powder, some of them involve large rods, like friction stir welding, and there are processes that involve binders too, and then sintering, kind of like the MIM process. So we fall into the wire category. In the case of this chart that was created by AM Power, it's a 3D printing consulting firm out of Germany, they categorize our technology under resistance welding. And there are a lot of and you can see kind of our logo there, Digital Alloys, on the right-hand side. There are a lot of companies in this space delivering all these different processes. But after 20 years, which is when metal 3D printing really started with laser powder bed, it's still a very niche process. You look at global metal manufacturing, something like a $3 trillion industry. Global metal 3D printing is less than 0.1%. So it's been used in some really interesting ways in aerospace, in medical, but the vast majority is still in R&D, and it's still in just rapid prototyping. And we've spoken to hundreds of manufacturers now, and the reasons we consistently hear are it's too expensive, it's too slow, it's too complex, and by complex, it's too hard to design for, it's too hard to qualify, it's too hard to integrate into our factories and deal with all the post-processing and so forth. And so in 1 second, I'll talk about how our technology works, but let me kind of frame it by kind of looking at three of the major ways to print metal today. The first is laser powder bed fusion. Some of you guys may be familiar with this. This is the original way to 3D print metal. It's about 20 years old. This is about 3/4 of the market today. You're using powders, which are expensive and can be considered dangerous because of the flammability risk and risk of inhalation. You're using machines with very advanced laser systems and process control systems machines are very expensive, the materials are very expensive, and they operate very slowly. You're talking about speeds of maybe around 0.1 kilograms an hour printing titanium. Then you have binder jetting machines. This is sort of a newer technology that it's also powder bed. It's also powdered metal, but they can actually take advantage of MIM powders, which are a little cheaper. But they are essentially using a binder, a glue, to build that green part. And then they either dissolve away the binder or they sinter it in a furnace, and then to kind of shrink and densify the part. Just like metal injection molding, we think it'll kind of make sense for small, complex parts. It really improves the speed and scalability of the process, but will probably not make sense for more structural aerospace type parts. And it's pretty hard to do with titanium too. Then there's direct energy deposition. Sayaki is here. I saw their booth. There are a lot of companies that do this now, but basically think of it as robotic welding. The processes that use wire typically use 2-3 millimeter wire, and then they have a very high energy heat source. They create kind of a large melt puddle, and they push that around to basically build up a part with a weld bead. It's very, it takes advantage of welding wire, which is great because it's low cost. It's widely available. They can process materials at pretty high speeds, 5 to 10 kilograms an hour. Some of these machines can go up to, but it's very low resolution. You don't have a lot of geometric complexity. It's made sense really for very large, simple kind of aerostructures and industrial parts. So what we do, Joule printing, and this video is in real time, is we take a wire, and I already mentioned some of those benefits. It's relatively low cost, it's safe, you can find it in a lot of different metals thanks to the welding industry. We take that wire, we touch it to the build plate, and then we push electric current through it. It's quite different than most people think, sort of arc welding. It's really differentiated from arc welding in the sense that there's no arc. We're pushing current directly through the wire, so we're using resistive heating, just like a coil in a toaster, to rapidly melt the tip of the metal wire in contact with the part. And as you can see, we can move very quickly in depositing that bead. So we're basically we're using roughly a millimeter wire. We're laying down a bead of metal that's about the same proportions as the wire. So we're printing with that wire size. We're printing titanium today. That video is at about 2 kilograms an hour. I'll show you another video, I think it's in here, where we're printing at about 4 kilograms an hour. We're printing steels and denser metals at 7-8 kilograms an hour. So we're really operating at sort of the very fastest of metal printing speeds, but with an order of magnitude better resolution than what you could get out of these welding type processes. It's in an inert atmosphere, argon. And so it's also very low energy compared to DED processes. Here, if you guys can squint and see, we're operating at about 2 volts across the wire. So, an AA battery of voltage, but high amps, so around 300 or so amps. But you do the math, voltage times current is power. At about 600 to 800 watts, we're forming parts at a couple kilograms an hour of titanium, which is another order of magnitude lower in energy than the typical welding process. And the benefits of that, energy is not that expensive. When you actually look at a part, you're talking about probably cents in terms of money. But the real benefit is in terms of material properties and grain structure. You look at a lot of metal printed parts, they have, especially with titanium, columnar grain growth. You have issues with anisotropic properties. You have issues that come out of these really high energy cycling. The residual stresses are also a big issue. A lot of times printing titanium, the part will sort of rip itself apart while you're printing it. And also because this is a closed circuit, we can measure exactly how much energy is going into the melt zone. We can measure exactly how much material is going into that voxel through precision wire feed. And with precision motion control, we know exactly where it is. And so we are able to do really advanced kind of closed loop direct measurement in a way that wasn't possible with most previous metal printing processes. So here's kind of just showing over the last year, well, let me try and cue this up again. Over the last year, you can see the advancement in speed that we've been able to achieve here, from about 1 kilogram an hour to about 4 kilograms an hour in titanium. And we've designed these first systems to actually go quite a bit faster than this even. It will depend on the part geometry, the true deposition rate that we can achieve. But this process doesn't have any sort of physical fundamental time constants, the way that a lot of other metal printing processes do, where you're kind of waiting on sort of to move heat to the right place. So in terms of properties, what do we actually get out of the process? I'll pass this around later, but here's sort of a part that's printed. We're printing a lot of these right now for material level testing, just a lot of coupons. This part, for a frame of reference, is printed in about 4.5 minutes. This is titanium. On a typical laser powder bed machine, which I mentioned is kind of the dominant approach today, this takes the better part of a day to print. So the colors don't come across very well, and this formatting looks to be a little weird on this slide. But basically, you can kind of see the bar that represents the joule printing Z strength. And that's typically the most challenging orientation, right, to pull the part in across the layers. But we're seeing very close to wrought properties from the minimum of a fairly large sample of coupons. So we're seeing not quite wrought yet, but we're getting there. We're still improving and refining the process and the software. But we're seeing very close to wrought properties right out of the printer, without any heat treatment, without any hipping, which is pretty standard for printing titanium with other processes. So we're excited about that. We're seeing really high density, 99.6% minimum density, again, without post-processing. And what you get in terms of surface finish is sort of similar to like a sand casting. Somewhere in the range of like 50 microns RA, surface roughness. So it's a near net shape process in almost all applications, right? It's like, think of it like casting. You're having to do some sort of finish machining to any sort of functional critical surfaces. But the benefit is that you can get to that near net shape very quickly, very efficiently, especially in materials like titanium, which are expensive, which are hard to process, which consume a lot of energy for material waste. So the process is, although we are focused on titanium and also tool steel as sort of our first two launch markets and applications, the process, what's exciting is we proved it's compatible with virtually any metal. Early on in development, we went out there and purchased something like 30 different types of metals, anywhere from really low resistivity metals like copper and aluminum to high resistivity metals, I guess like titanium. And really dense metals, low density metals, all sorts of different alloys. And we were able to print every single wire we put into the printer, at least as just a little block, a proof of concept that it was compatible. But now in terms of focus, in terms of sort of commercialization, we're starting with these two. Inconel 718 will be the next material we release. And then we're looking at a lot of other alloys and grades of metals that are in this sort of same category, again, of high cost, hard to process. I'll just kind of put this on your radar. This is sort of on the back burner for now. It's sort of an R&D project, but we do also have this unique capability to combine different metals into one part. The wire feed system is built in sort of a treed system where you can retract one wire and insert another into that same print head. And so this is just a crude proof of concept, just one metal on top of the other. But in theory, in the future, we'll be able to switch between wires within each layer and produce some very complex multi-metal parts, which can, it's sort of a, mechanical, electrical engineer's sort of dream, right? They can achieve all sorts of different properties in a really optimized way through design. So this is hard to see, but let me kind of talk you through it a little bit. So we've done a lot of analysis into cost structures of metal printing, because this has been one of the biggest obstacles with adoption. And looking at titanium, we took sort of a typical geometry, a fairly complex part that would be expensive or hard to machine. And we looked at a 1 kilogram titanium part and the different costs from printing to materials to post-processing. And laser powder bed, actually I'm going to forget the numbers now, is in the range of like $1,500 to produce a finished machined 1 kilogram titanium part. DED processes are a lot more efficient, but they also, because they're very low resolution, kind of like a forging, there's still a lot of material to remove. So for those reasons, because of the wire is still quite a bit more expensive than billet, you can see they're still fairly expensive. And then dual printing, you can see at the bottom there, because we're able to print very quickly using wire and get very close to the near net shape. We achieve a very accurate, a very successful kind of cost structure. And I think in the interest of time, I'll skip over kind of going further into our cost structure. If anyone's interested, I'm happy to share this after the presentation. As a company, we are very open about the true costs of printing with our technology. We think that's going to be key to adoption. But yeah, again, I can go over that with anyone that's interested. But here's one sort of aerospace example that we're allowed to share. This is a fuselage bracket with an aerospace OEM that we're working with. And there are a lot of different parts in the plane that look like this. And early on in production, they often start machined from billet, which is kind of represented there in that wire frame. So in this case, the supplier to this OEM takes a 6.8 kilogram block of titanium and machines away 94% of that material. And again, to go back to Reed's talk, right, we looked at how much energy is consumed in the primary metal manufacturing. If you can't efficiently recycle all of that scrap, which you can't with titanium, that's a ton of energy waste. Not to mention the cost, right? The cost of the material and the cost of machining. So this actually ends up being something like $1,000 part for this aerospace company today. We can print the near net shape in about 12 minutes. We can do the finished machining in about 30 minutes, and we can produce this part for about a third of the cost. Granted, like I said before, the caveat is this is still very much in development, right? So we're very excited about the potential to do this. This part's not being produced or flying in a plane today. We know that that takes a long time. Here's a quick view of just the printer to give you guys an idea. Like I said, we're still kind of in beta. We have a few of these machines built today that we're printing parts for customers with, but we plan to start selling these in a couple of years. You can see the build volume there. In inches, if that's how you guys operate, it's about 16 by 16 by 10 inches. We think of kind of like a beach ball sort of size. If you can fit your part in there, you can print it in this first machine. But this technology really, dual printing really inherently scales very well, just like these large welding approaches. So we are thinking, of course, if we're successful with our first product and get the opportunity to launch another one, that we will be building much larger machines in the future. And just a quick view of some of our early access customers and partners that have allowed us to share their logo. So that's it for me. I think I'm doing okay on time. Thank you.